Welcome back, everybody. I'm sure you've noticed, but there's been a lot of cool activity on the forum this week. And one of the things that's been really great to see is that a lot of you have started creating really helpful materials, both for your classmates to better understand stuff and also for you to better understand stuff by trying to teach what you've learned. I just wanted to highlight a few. I've actually posted to the wiki thread a few of these, but there's lots more. Reshima's posted a whole bunch of nice introductory tutorials. So, for example, if you're having any trouble getting connected with AWS, she's got a whole step-by-step how to go about logging in and getting everything working, which I think is a really terrific thing. And so it's a kind of thing that if you are writing some notes for yourself to remind you how to do it, you may as well post them for others to do it as well. And by using a markdown file like this, it's actually good practice if you haven't used GitHub before. If you put it up on GitHub, everybody can now use it. Or, of course, you can just put it in the forum. More advanced thing that Reshima wrote up about is she noticed that I like using tmux, which is a handy little thing which lets me basically have a window. Let's see if I've got one. I'll show you. So as soon as I log into my computer, if I run tmux, you'll see that all of my windows pop straight up, basically, and I can continue running stuff in the background, and I can I've got Vim over here, and I can kind of zoom into it, or I can move over to the top, which is here's my Jupyter kernel running, and so forth. So if that sounds interesting, Reshima has a tutorial here on how you can use tmux. And she's actually got a whole bunch of stuff in her GitHub, so that's really cool. Uphill Tamang has written a very nice kind of summary, basically, of our last lesson, which kind of covers what are the key things we did and why did we do them. So if you're kind of wondering how does it fit together, I think this is a really helpful summary of what did those couple of hours look like if we summarize it all into a page or two. I also really like Pavel has done a deep dive on the learning rate finder, which is a topic that a lot of you have been interested in learning more about, particularly those of you who have done deep learning before. Have realized that this is like a solution to a problem that you've been having for a long time and haven't seen before, and so it's kind of something which hasn't really been blogged about before. So this is the first time I've seen this blogged about. So when I put this on Twitter, a link to Pavel's post, it's been shared now hundreds of times. It's been really, really popular and viewed many thousands of times. So that's some great content. Radek has posted lots of cool stuff. I really like this Practitioner's Guide to PyTorch, which, again, this is more for more advanced students, but it's like digging into people who have never used PyTorch before but know a bit about numerical programming in general. It's a quick introduction to how PyTorch is different. And then there's been some interesting little bits of research, like what's the relationship between learning rate and batch size? So one of the students actually asked me this before class, and I said, well, one of the other students has written an analysis of exactly that. So what he's done is basically looked through and tried different batch sizes and different learning rates and tried to see how they seem to relate together. And these are all cool experiments which you can try yourself. Radek again, he's written something, again, a kind of a research into this question. I made a claim that the stochastic gradient descent with restarts finds more generalizable parts of the function surface because they're kind of flatter. And he's been trying to figure out, is there a way to measure that more directly? Not quite successful yet, but a really interesting piece of research. Got some introductions to convolutional neural networks. And then something that we'll be learning about towards the end of this course, but I'm sure you've noticed we're using something called ResNet, and Anand Sahar actually posted a pretty impressive analysis of what's a ResNet and why is it interesting. And this one's actually been already shared very widely around the internet, I've seen also. So more advanced students who are interested in jumping ahead can look at that. And Uphill to Mung also has done something similar. So lots of stuff going on the forums. I'm sure you've also noticed we have a beginner forum now specifically for asking questions, which there's always the case that there are no dumb questions, but when there's lots of people around you talking about advanced topics, it might not feel that way. So hopefully the beginners forum is just a less intimidating space. And if you're a more advanced student who can help answer those questions, please do. But remember, when you do answer those questions, try to answer in a way that's friendly to people that maybe, have no more than a year of programming experience and haven't done any machine learning before. So I hope other people in the class feel like you can contribute as well. And just remember, all of the people we just looked at, or many of them, I believe, have never posted anything to the internet before, right? I mean, you don't have to be a particular kind of person to be allowed to blog or something. You can just jot down your notes, throw it up there. And one handy thing is if you just put it on the forum and you're not quite sure of some of the details, then you have an opportunity to get feedback and say like, well, that's not quite how that works. Actually it works this way instead, or that's a really interesting insight. Had you thought about taking this further, and so forth. So what we've done so far is a kind of an introduction as a practitioner to convolutional neural networks for images. And we haven't really talked much at all about the theory or why they work or the math of them. But on the other hand, what we have done is seen how to build a model which actually works exceptionally well, in fact, world-class level models. And we'll kind of review a little bit of that today. And then also today we're going to dig in a little bit, quite a lot more actually, into the underlying theory of like what is a CNN, what's a convolution, how does this work, and then we're going to kind of go through this cycle where we're going to do a little intro into a whole bunch of application areas using neural nets for structured data, so kind of like logistics or forecasting or financial data or that kind of thing, and then looking at language applications, NLP applications using recurrent neural nets, and then collaborative filtering for recommendation systems. And so these will all be like similar to what we've done for CNNs for images. It'll be like, here's how you can get a state-of-the-art result without digging into the theory, but knowing how to actually make it work. And then we're kind of going to go back through those almost in reverse order. So then we're going to dig right into collaborative filtering in a lot of detail and see how to write the code underneath and how the math works underneath. And then we're going to do the same thing for structured data analysis. We're going to do the same thing for ConvNets for images. And finally, an in-depth deep dive into recurrent neural networks. So that's kind of where we're heading. So let's start by doing a little bit of a review. And I want to also provide a bit more detail on some steps that we only briefly skipped over. So I want to make sure that we're all able to complete kind of last week's assignment, which was the dog breeds. I mean, to basically apply what you've learned to another data set, and I thought the easiest one to do would be the dog breeds Kaggle competition. And so I want to make sure everybody has everything you need to do this right now. So the first thing is to make sure that you know how to download data. And so there's two main places at the moment we're kind of downloading data from. One is from Kaggle, and the other is from like anywhere else. And so I'll first of all do the Kaggle version. So to download from Kaggle, we use something called Kaggle CLI, which is here. And to install it, I think it's already in. Let's just double check. Yeah, so it should already be in your environment. But to make sure, one thing that happens is because this is downloading from the Kaggle website through like screen scraping, every time Kaggle changes the website, it breaks. So anytime you try to use it, and if the Kaggle website's changed recently, you'll need to make sure you get the most recent version. So you can always go pip install Kaggle-CLI -- upgrade. And so that'll just make sure that you've got the latest version of it and everything that it depends on. Okay. And so then having done that, you can follow the instructions. Actually, I think Reshima was kind enough to, there you go, there's a Kaggle CLI. I feel like everything you need to know can be found at Reshima's GitHub. So basically, to do that, to the next step, you go kg download, and then you provide your username with -u. You provide your password with -p. And then -c, you need the competition name. And a lot of people in the forum has been confused about what to enter here. And so the key thing to note is that when you're at a Kaggle competition, after the /c, there's a specific name, planet-understanding-, etc. Right? That's the name you need. Okay. The other thing you'll need to make sure is that you've, on your own computer, have attempted to click download at least once, because when you do, it'll ask you to accept the rules. If you've forgotten to do that, kg download will give you a hint. It'll say, oh, it looks like you might have forgotten the rules. If you log into Kaggle with like a Google account, like anything other than a username and password, this won't work. So you'll need to click forgot password on Kaggle and get them to send you a normal password. So that's the Kaggle version, right? And so when you do that, you end up with a whole folder created for you with all of that competition data in it. So a couple of reasons you might want to not use that. The first is that you're using a data set that's not on Kaggle. The second is that you don't want all of the data sets in a Kaggle competition. For example, the planet competition that we've been looking at a little bit, we'll look at again today, has data in two formats, TIFF and JPEG. The TIFF is 19 gigabytes and the JPEG is 600 megabytes. So you probably don't want to download both. So I'll show you a really cool kit, which actually somebody on the forum taught me. I think it was one of the MSAN students here at USF. There's a Chrome extension called curl wget. So you can just search for curl wget. And then you install it by just clicking on install if you haven't installed an extension before. And then from now on, every time you try to download something, so I'll try and download this file. And I'll just go ahead and cancel it, right? And now you see this little yellow button that's added up here. There's a whole command here, right? So I can copy that and paste it into my window and hit go, and there it goes. Okay, so what that does is like all of your cookies and headers and everything else needed to download that file is like saved. So this is not just useful for downloading data. It's also useful if you're like trying to download some, I don't know, TV show or something, anything where you're hidden behind a login or something. You can grab it. And actually that is very useful for data science because quite often we want to analyze things like videos on our consoles. So this is a good trick. All right, so there's two ways to get the data. So then, having got the data, you then need to build your model, right? So what I tend to do, like you'll notice that I tend to assume that the data is in a directory called data, that's a subdirectory of wherever your notebook is, right? Now, you don't necessarily actually want to put your data there. You might want to put it directly in your home directory, or you might want to put it on another drive or whatever. So what I do is if you look inside my courses DL1 folder, you'll see that data is actually a symbolic link to a different drive, right? So you can put it anywhere you like, and then you can just add a symbolic link. Or you can just put it there directly. It's up to you. If you haven't used symlinks before, they're like aliases or shortcuts on the Mac or Windows. Very handy, and there's some threads on the forum about how to use them if you want help with that. That, for example, is also how we actually have the Fast AI modules available from the same place as our notebooks. It's just a symlink to where they come from. Anytime you want to see like where things actually point to in Linux, you can just use the -L flag. to listing a directory, and that'll show you where the symlinks exist. It'll also show you which things are directories, so forth. Okay, so one thing which may be a little unclear based on what we've done so far is like how little code you actually need to do this end-to-end. So what I've got here is in a single window is an entire end-to-end process to get a state-of-the-art result for cats versus dogs, right? The only step I've skipped is the bit where we've downloaded it from Kaggle and then where we've unzipped it, right? So these are literally all the steps. And so we import our libraries. And actually, if you import this one, conv learner, that basically imports everything else. So that's that. We need to tell it the path of where things are, the size that we want, the batch size that we want, right? So then, and we're going to learn a lot more about what these do very shortly, but basically we say, how do we want to transform our data? So we want to transform it in a way that's suitable to this particular kind of model, and that assumes that the photos are side-on photos, and that we're going to zoom in up to 10% each time. We say that we want to get some data based on paths. And so remember, this is this idea that there's a path called cats and a path called dogs, and they're inside a path called train and a path called valid. Note that you can always overwrite these with other things. So if your things are in different named folders, you could either rename them, or you can see here there's like a train name and a val name. You can always pick something else here. Also notice there's a test name. So if you want to submit something to Kaggle, you'll need to fill in the name of the folder where the test set is. And obviously those won't be labeled. So then we create a model from a pre-trained model. It's from a ResNet 50 model using this data. And then we call fit. And remember, by default, that has all of the layers but the last few frozen. And again, we'll learn a lot more about what that means. And so that's what that does. So that took 2.5 minutes. Notice here I didn't say pre-compute equals true. Again, there's been some confusion on the forums about like what that means. It's only something that makes it a little faster for this first step, right? So you can always skip it. And if you're at all confused about it or it's causing you any problems, just leave it off, right? Because it's just a shortcut which caches some of the intermediate steps that don't have to be recalculated each time. Okay? And remember that when we are using pre-computed activations, data augmentation doesn't work, right? So even if you ask for a data augmentation, if you've got pre-compute equals true, it doesn't actually do any data augmentation because it's using the cached, non-augmented activations. So in this case, to keep this as simple as possible, I have no pre-computed anything going on. So I do 3 cycles of length 1, and then I can then unfreeze. So it's now got to train the whole thing. Something we haven't seen before and we'll learn about in the second half is called BN freeze. For now, all you need to know is that if you're using a model, like a bigger, deeper model like ResNet 50 or ResNext 101, on a data set that's very, very similar to ImageNet, like this cats and dogs data set. So in other words, it's like side-on photos of standard objects, you know, of a similar size to ImageNet, like somewhere between 200 and 500 pixels. You should probably add this line when you unfreeze. For those of you that are more advanced, what it's doing is it's causing the batch normalization, moving averages to not be updated. But in the second half of this course, you're going to learn all about why we do that. It's something that's not supported by any other library, but it turns out to be super important. Anyway, so we do one more epoch with training the whole network. And then at the end, we use test time augmentation to ensure that we get the best predictions we can. And that gives us 99.45%. So that's it, right? So when you try a new data set, they're basically the minimum set of steps that you would need to follow. You'll notice this is assuming I already know what learning rate to use, so you'd use the learning rate finder for that. It's assuming that I know the directory layout, and so forth. So that's kind of a minimum set. Now, one of the things that I wanted to make sure you had an understanding of how to do is how to use other libraries other than FastAI. And so I feel like the best thing to look at is to look at Keras, because Keras is a library, just like FastAI sits on top of PyTorch, Keras sits on top of actually a whole variety of different backends. It fits, mainly people nowadays use it with TensorFlow. There's also an MXNet version. There's also a Microsoft CNTK version. So what I've got, if you do a git pull, you'll see that there's a something called Keras lesson 1, where I've attempted to replicate at least parts of lesson 1 in Keras. Just to give you a sense of how that works. Yeah.
In the previous one, can you tell us about the batch normalization?
I'm not going to talk more about batch norm freeze now, other than to say if you're using something which has got a number larger than 34 at the end, so like ResNet 50 or ResNext 101, and you're training a data set that is very similar to ImageNet, so it's like normal photos of normal sizes where the thing of interest takes up most of the frame, then you probably should add bn freeze true after unfreeze. If in doubt, try training it with and then try training it without. More advanced students can certainly talk about it on the forums this week, and we will be talking about the details of it in the second half of the course when we come back to our CNN in depth section in the second last lesson. So with Keras, again, we import a bunch of stuff, and remember I mentioned that this idea that you've got a thing called train and a thing called valid, and inside that you've got a thing called dogs and a thing called cats, is a standard way of providing labeled images. So Keras does that too, right? So it's going to tell it where the training set and the validation set are. I've got batch size twice. What batch size to use. Now you'll notice in Keras we need much, much, much more code to do the same thing. More importantly, each part of that code has many, many, many more things you have to set, and if you set them wrong, everything breaks, right? So I'll give you a summary of what they are. So you basically, rather than creating a single data object in Keras, we first of all have to define something called a data generator to say how to generate the data. And so a data generator, we basically have to say, what kind of data augmentation do we want to do? And we actually have to say what kind of normalization do we want to do. So where else with FastAI, we just say, whatever ResNet 50 requires, just do that for me, please. We actually have to kind of know a little bit about what's expected of us. Generally speaking, copying and pasting Keras code from the internet is a good way to make sure you've got the right stuff to make that work. And again, it doesn't have a kind of a standard set of like, here are the best data augmentation parameters to use for photos. So, I've copied and pasted all of this from the Keras documentation. So I don't know if I don't think it's the best set to use at all, but it's the set that they're using in their docs. So having said this is how I want to generate data, so horizontally flip sometimes, zoom sometimes, shear sometimes. We then create a generator from that by taking that data generator and saying, I want to generate images by looking from a directory. And we pass in the directory, which is of the same directory structure that FastAI uses. And you'll see there's some overlaps with kind of how FastAI works here. You tell it what size images you want to create. You tell it what batch size you want in your mini batches. And then there's something here not to worry about too much, but basically if you're just got two possible outcomes, you would generally say binary here. If you've got multiple possible outcomes, you would say categorical. Yeah. So we've only got cats or dogs, so it's binary. So an example of like where things get a little more complex is you have to do the same thing for the validation set. So it's up to you to create a data generator that doesn't have data augmentation, because obviously for the validation set, unless you're using TTA, that's going to stuff things up. You also when you train, you randomly reorder the images so that they're always shown in different orders to make it more random. But with the validation, it's vital that you don't do that, because if you shuffle the validation set, you then can't track how well you're doing because it's in a different order to the labels. Right? So basically, these are the kind of steps you have to do every time with Keras. So again, the reason I was using ResNet 50 before is Keras doesn't have ResNet 34, unfortunately. So I just wanted to compare like with like. So we've got to use ResNet 50 here. There isn't the same idea with Keras of saying like construct a model that is suitable for this data set for me. So you have to do it by hand, right? So the way you do it is to basically say, this is my base model. And then you have to construct on top of that manually the layers that you want to add. And so by the end of this course, you'll understand why it is that these particular 3 layers are the layers that we add. So having done that in Keras, you basically say, okay, this is my model. And then again, there isn't like a concept of like automatically freezing things or an API for that. So you just have to loop through the layers that you want to freeze and call .trainable equals false on them. In Keras, there's a concept we don't have in FastAI or PyTorch of compiling a model. So basically, once your model's ready to use, you have to compile it, passing in what kind of optimizer to use, what kind of loss to look for, and what metrics. So again, with FastAI, you don't have to pass this in because we know what loss is the right loss to use. You can always override it, but for a particular model, we give you good defaults. Okay, so having done all that, rather than calling fit, you call fit generator, passing in those 2 generators that you saw earlier, the train generator and the validation generator. For reasons I don't quite understand, Keras expects you to also tell it how many batches there are per epoch. So the number of batches is equal to the size of the generator divided by the batch size. You can tell it how many epochs. Just like in FastAI, you can say how many processes or how many workers to use for pre-processing. Unlike FastAI, the default in Keras is basically not to use any. So to get good speed, you're going to make sure you include this. And so that's basically enough to start fine-tuning the last layers. So as you can see, I got to a validation accuracy of 95%. But as you can also see, something really weird happened where after 1, it was like 49, and then it was 69, and then 95. I don't know why these are so low. That's not normal. There may be a bug in Keras. There may be a bug in my code. I reached out on Twitter to see if anybody could figure it out, but they couldn't. I guess this is one of the challenges with using something like this. Is one of the reasons I wanted to use FastAI for this course. Is it's much harder to screw things up. So I don't know if I screwed something up or somebody else did. Yes, you know.
I wonder, are you using
This is using the TensorFlow backend. Yeah. And if you want to run this to try it out yourself, you just can go pip install TensorFlow-GPU Keras. Okay, because it's not part of the FastAI environment by default. But that should be all you need to do to get that working. So then there isn't a concept of like layer groups or differential learning rates or partial unfreezing or whatever. So you have to decide, like I had to print out all of the layers and decide manually how many I wanted to fine tune. So I decided to fine tune everything from a layer 140 onwards. So that's why I just looped through like this. After you change that, you have to recompile the model. And then after that, I then ran another step. And again, I don't know what happened here. The accuracy of the training set stayed about the same, but the validation set totally fell in a hole. But I mean, the main thing to note is even if we put aside the validation set, we're getting, I mean, I guess the main thing is there's a hell of a lot more code here, which is kind of annoying, but also the performance is very different. So we're also here, even on the training set, we were getting like 97% after 4 epochs that took a total of about 8 minutes. You know, over here we had 99.5% on the validation set, and it ran a lot faster. So it was like 4 or 5 minutes, right? So depending on what you do, particularly if you end up wanting to deploy stuff to mobile devices, at the moment, the kind of PyTorch on mobile situation is very early. So you may find yourself wanting to use TensorFlow, or you may work for a company that's kind of settled on TensorFlow. So if you need to convert something, like redo something you've learned here in TensorFlow, you probably want to do it with Keras, but just recognize, it's going to take a bit more work to get there. And by default, it's much harder to get. I mean, to get the same state-of-the-art results you get with FastAI, you'd have to like replicate all of the state-of-the-art algorithms that are in FastAI. So it's hard to get the same level of results. But you can see the basic ideas are similar. Okay, and it's certainly possible. Like there's nothing I'm doing in FastAI that like would be impossible, but like you would have to implement stochastic gradient descent with restarts. You would have to implement differential learning rates. You would have to implement batch norm freezing, blah, 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 which you probably don't want to do. I know, well, that's not quite true. I think one person, at least on the forum, is attempting to create a Keras compatible version of, or a TensorFlow compatible version of FastAI, which I hope we'll get there. I actually spoke to Google about this a few weeks ago, and they're very interested in getting FastAI ported to TensorFlow. So maybe by the time you're looking at this on the MOOC, maybe that'll exist. I certainly hope so. We will see. Anyway, so Keras and TensorFlow are certainly not, that difficult to handle, and so I don't think you should worry if you're told you have to learn them after this course. For some reason, it'll only take you a couple of days, I'm sure. So that's kind of most of the stuff you would need to kind of complete this kind of assignment from last week, which was like try to do everything you've seen already, but on the dog breeds data set. And just to remind you, the kind of last few minutes of last week's lesson, I show you how to do much of that, including like how I actually explored the data to find out like what the classes were and how big the images were and stuff like that, right? So if you've forgotten that or didn't quite follow it all last week, check out the video from last week to see. One thing that we didn't talk about is how do you actually submit to Kaggle? So how do you actually get predictions? So I just wanted to show you that last piece as well. And on the wiki thread this week, I've already put a little image of this to show you these steps. But if you go to the Kaggle website, for every competition, there's a section called Evaluation, and they tell you what to submit. And so I just copied and pasted these 2 lines from there. And so it says, we're expected to submit a file where the first line contains the word ID, and then a comma-separated list of all of the possible dog breeds. And then every line after that will contain the ID itself, followed by all the probabilities of all the different dog breeds. So how do you create that? So recognize that inside our data object, there's a .classes, which has got in alphabetical order all of the classes. And then, so it's got all of the different classes. And then inside data.test dataset, test.ds, you can also see there's all the file names. And just to remind you, dogs and cats, sorry, not dogs and cats, dog breeds was not provided in the kind of Keras style format where the dogs and cats are in different folders, but instead it was provided as a CSV file of labels, right? So when you get a CSV file of labels, you use image classifier data from CSV rather than image classifier data from paths. There isn't an equivalent in Keras, so you'll see like on the Kaggle forums, people share scripts for how to convert it to a Keras style folders, but in our case, we don't have to. We just go image classifier data from CSV, passing in that CSV file. And so the CSV file will, has automatically told the data, what the classes are. And then also we can see from the folder of test images what the file names of those are. So with those two pieces of information, we're ready to go. So I always think it's a good idea to use TTA. As you saw with that dogs and cats example just now, it can really improve things, particularly when your model is less good. So I can say learn.tta, and if you pass in here, if you pass in is test equals true, then it's going to give you predictions on the test set rather than the validation set. Okay, and now obviously we can't now get an accuracy or anything, because by definition we don't know the labels for the test set, right? So by default, most PyTorch models give you back the log of the predictions. So then we just have to go exp of that to get back our probabilities. So in this case, the test set had 10,357 images in it, and there are 120 possible breeds. Right? So we get back a matrix of that size. And so we now need to turn that into something that looks like this. And so the easiest way to do that is with pandas. If you're not familiar with pandas, there's lots of information online about it, or check out the machine learning course, Intro to Machine Learning, that we have, where we do lots of stuff with pandas. But basically, we can just go pd.dataframe and pass in that matrix, and then we can say the names of the columns are equal to data.classes. And then finally, we can insert a new column at position 0 called ID that contains the file names. But you'll notice that the file names contain 5 letters at the end, a start we don't want, and 4 letters at the end we don't want. So I just subset in like so, right? So at that point, I've got a data frame that looks like this, which is what we want. So you can now call data frame data. I should have used df, not ds. Let's fix it now. Data frame. Okay, so you can now call data frame to CSV, and quite often you'll find these files actually get quite big. So it's a good idea to say compression equals gzip, and that'll zip it up on the server for you. And that's going to create a zipped up CSV file on the server, on wherever you're running this Jupyter notebook. So you now need to get that back to your computer so you can upload it. Or you can use Kaggle CLI. So you can type kg submit and do it that way. I generally download it to my computer because I often like to just double check it all looks okay. So to do that, there's a cool little thing called file link. And if you run file link with a path on your server, it gives you back a URL which you can click on, and it'll download that file from the server onto your computer. So if I click on that now, I can go ahead and save it, and then I can see in my downloads, there it is. Here's my submission file. Taking a while to open. There we are. And as you can see, it's exactly what I asked for. There's my ID and the 120 different dog breeds. And then here's my first row containing the file name and the 120 different probabilities. Okay, so then you can go ahead and submit that to Kaggle through their regular form. And so this is also a good way. You can see we've now got a good way of both grabbing any file off the internet and getting it to our AWS instance or Paperspace or whatever by using the cool little extension in Chrome. And we've also got a way of grabbing stuff off our server easily. Those of you that are more command line oriented, you can also use SCP, of course. But I kind of like doing everything through the notebook. All right. One other question I had during the week was what if I want to just get a single file that I want to, get a prediction for? So, for example, maybe I want to get this first file from my validation set. So there's its name. So you can always look at a file just by calling image.open. That just uses the regular Python imaging library. And so what you can do is, there's actually, I'll show you the shortest version. You can just call learn.predictArray, passing in your image. Okay. Now the image needs to have been transformed. So you've seen transforms from model before. Normally we just put it all in one variable, but actually behind the scenes it was returning two things. It was returning training transforms and validation transforms. So I can actually split them apart. And so here you can see I'm actually applying, for example, my training transforms, or probably more likely I would apply validation transforms. That gives me back an array containing the image, the transformed image, which I can then pass to predict array. Everything that gets passed to or returned from our models is generally assumed to be a mini batch, right? It's generally assumed to be a bunch of images. So we'll talk more about some NumPy tricks later, but basically in this case, we only have one image, so we have to turn that into a mini batch of images. So in other words, we need to create a tensor that basically is not just rows by columns by channels, but it's number of image by rows by columns by channels, and it has one image. So it basically becomes a four-dimensional tensor. So there's a cool little trick in NumPy that if you index into an array with none, that basically adds an additional unit access to the start. So it turns it from an image into a mini batch of one images. And so that's why we had to do that. So if you basically find you're trying to do things with a single image, with any kind of PyTorch or FastAI thing, this is just something you might find. It says like expecting 4 dimensions, only got 3. It probably means that. Or if you get back a return value from something that has like some weird first axis, that's probably why. It's probably giving you like back a mini batch. Okay, and so we'll learn a lot more about this, but it's just something to be aware of. Okay, so that's kind of everything you need to do in practice. So now we're going to kind of get into a little bit of theory. What's actually going on behind the scenes with these convolutional neural networks. And you might remember back in lesson 1, we actually saw our first little bit of theory, which we stole from this fantastic website, satosa.io EV, explained visually. And we learned that a convolution is something where we basically have a little matrix, in deep learning, nearly always 3 by 3, a little matrix that we basically multiply every element of that matrix by every element of a 3 by 3 section of an image, add them all together to get the result of that convolution at one point. Right? Now, let's see how that all gets turned together to create these various layers that we saw in the Zeiler and Burgess paper. And to do that, again, I'm going to steal off somebody who's much smarter than I am. We're going to steal from a guy called Ottavio Good. Ottavio Good was the guy who created WordLens, which nowadays is part of Google Translate. If on Google Translate you've ever like done that thing where you point your camera at something which has any kind of foreign language on it, and in real time it overlays it with a translation, that was Ottavio's company that built that. And so Ottavio was kind enough to share this fantastic video he created. He's at Google now. And I want to kind of step you through it because I think it explains really, really well what's going on. And then after we look at the video, we're going to see how to implement a whole sequence of an entire set of layers of convolutional neural network in Microsoft Excel. So whether you're a visual learner or a spreadsheet learner, hopefully you'll be able to understand all this. Right. So we're going to start with an image, and something that we're going to do later in the course is we're going to learn to recognize digits, and we'll do it like end to end. We'll do the whole thing. So this is pretty similar. So we're going to try and recognize, in this case, letters. So here's an A, which obviously it's actually a grid of numbers, right? And so there's the grid of numbers. And so what we do is we take our first convolutional filter. So we're assuming, this is assuming that these are already learnt, right? And you can see this one, it's got white down the right-hand side, right? And black down the left. So it's like 0, 0, 0, or maybe -1, -1, -1, 0, 0, 0, 1, 1, 1. And so we're taking each 3 by 3 part of the image and multiplying it by that 3 by 3 matrix. Not as a matrix product, but an element-wise product. And so you can see what happens is everywhere where the white edge is matching the edge of the A and the black edge isn't, we're getting green, we're getting a positive. And everywhere where it's the opposite, we're getting a negative, we're getting a red, right? And so that's the first filter, creating the first, the result of the first kernel, right? And so here's a new kernel. This one is got a white stripe along the top, right? So we literally scan it through every 3 by 3 part of the matrix, multiplying those 3 bits of the A, the 9 bits of the A by the 9 bits of the filter to find out whether it's red or green and how red or green it is. Okay? And so this is assuming we had 2 filters. One was a bottom edge, one was a left edge, and you can see here, the top edge, not surprisingly, it's red here. Sorry, bottom edge was red here and green here. The right edge, red here and green here. And then at the next step, we add a nonlinearity, okay, the rectified linear unit, which literally means throw away the negatives. So here, the red's all gone. Okay, so here's layer 1, the input. Here's layer 2, the result of 2 convolutional filters. Here's layer 3, which is throw away all of the red stuff, and that's called a rectified linear unit. And then layer 4 is something called a max pull. And on layer 4, we replace every 2 by 2 part of this grid, and we replace it with its maximum. Right? So it basically makes it half the size. It's basically the same thing, but half the size. And then we can go through and do exactly the same thing. We can have some new filter, 3 by 3 filter, that we put through each of the 2 results of the previous layer. Okay? And again, we can throw away the red bits, right? So get rid of all the negatives, so we just keep the positives. That's called applying a rectified linear unit. And that gets us to our next layer of this convolutional neural network. So you can see that by, at this layer back here, it was kind of very interpretable. It's like we've either got bottom edges or left edges. But then the next layer was combining the results of convolution. So it's starting to become a lot less clear, like intuitively what's happening. But it's doing the same thing. And then we do another max pull, right? So we replace every 2 by 2 or 3 by 3 section with a single digit. So here, this 2 by 2, it's all black. So we replaced it with a black, right? And then we go and we take that and we compare it to basically a kind of a template of what we would expect to see if it was an A, if it was a B, if it was a C, if it was a D, if it was an E. And we see how closely it matches. And we can do it in exactly the same way. We can multiply every one of the values in this 4 by 8 matrix with every one of the 4 by 8 in this one, and this one, and this one, and we just add them together to say, like, how often does it match versus how often does it not match? And then that can be converted to give us a percentage probability that this is an A. So in this case, this particular template matched well with A. So notice we're not doing any training here, right? This is how it would work if we have a pre-trained model. Right, so when we download a pre-trained ImageNet model off the internet and use it on an image without any changing to it, this is what's happening. Or if we take a model that you've trained and you're applying it to some test set or to some new image, this is what it's doing, right? Is it's basically taking it through, it's applying a convolution to each layer, multiple convolutional filters to each layer, and then doing the rectified linear unit, so throw away the negatives, and then do the max pull, and then repeat that a bunch of times. And so then we can do it with a new letter A or letter B or whatever, and keep going through that process, right? So as you can see, that's a far nicer visualization than I could have created because I'm not Ottavio. So thanks to him for sharing this with us because it's totally awesome. This is not done by hand. He actually wrote a piece of computer software to actually do these convolutions. This is actually being actually being done dynamically, which is pretty cool. So I'm more of a spreadsheet guy personally. I'm a simple person. So here is the same thing now in spreadsheet form, right? And so you'll find this in the GitHub repo. So you can either git clone the repo to your own computer to open up the spreadsheet, or you can just go to github.com/fastai and click on this. It sits inside if you go to our repo and just go to courses as usual, go to DL1 as usual, you'll see there's an Excel section there, okay? And so here they all are. So you can just download them by clicking them, or you can clone the whole repo. And we're looking at convolution example, right? So you can see I have here an input, right? So in this case, the input is the number 7. So I grabbed this from a data set called MNIST, M-N-I-S-T, which we'll be looking at in a lot of detail. And I just took one of those digits at random and I put it into Excel. And so you can see every pixel is actually just a number between 0 and 1. Okay? Very often, actually, it'll be a byte between 0 and 255, or sometimes it might be a float between 0 and 1. It doesn't really matter. By the time it gets to PyTorch, we're generally dealing with floats. So if one of the steps we often will take will be to convert it to a number between 0 and 1. So then you can see I've just used conditional formatting in Excel to kind of make the higher numbers more red. So you can clearly see that this is a red, that this is a 7, but it's just a bunch of numbers that have been imported into Excel. Okay, so here's our input. So remember what Ottavio did was he then applied 2 filters, right, with different shapes. So here I've created a filter which is designed to detect top edges. So this is a 3x3 filter, okay, and I've got 1s along the top, 0s in the middle, -1s at the bottom, right? So let's take a look at an example that's here, right? And so if I hit F2, you can see here highlighted, this is the 3x3 part of the input that this particular thing is calculating, right? So here you can see it's got 1, 1, 1 are all being multiplied by 1, and 0.100 are all being multiplied by -1. Okay, so in other words, all the positive bits are getting a lot of positive, the negative bits are getting nearly nothing at all, so we end up with a high number. Okay? Whereas on the other side of this bit of the 7, right, you can see how, this is basically zeros here, or perhaps more interestingly, on the top of it, right, here we've got high numbers at the top, but we've also got high numbers at the bottom, which are negating it. Okay, so you can see that the only place that we end up activating is where we're actually at an edge. Okay. So in this case, this number 3, this is called an activation. Okay, so when I say an activation, I mean a number that is calculated. And it is calculated by taking some numbers from the input and applying some kind of linear operation, in this case a convolutional kernel, to calculate an output. Right? You'll notice that other than going inputs multiplied by kernel and summing it together, right? So here's my sum, and here's my multiply. I then take that and I go max of 0, that. And so that's my rectified linear unit. So it sounds very fancy, rectified linear unit, but what they actually mean is open up Excel and type equals max 0, thing. Okay? That's all and you'll see people in the biz, they'll just say ReLU. Okay, so ReLU means rectified linear unit, means max 0, thing. And I'm not like simplifying it, I really mean it. Like when I say, like if I'm simplifying, I'll always say I'm simplifying. But if I'm not saying I'm simplifying, that's the entirety. Okay, so a rectified linear unit in its entirety is this. And a convolution in its entirety is this. Okay, so a single layer of a convolutional neural network is being implemented in its entirety here in Excel. Okay, and so you can see what it's done is it's deleted pretty much the vertical edges and highlighted the horizontal edges. So again, this is assuming that our network is trained and that at the end of training it had created a convolutional filter with these specific 9 numbers in. And so here is a second convolutional filter. It's just a different 9 numbers. Now, PyTorch doesn't store them as 2 separate 9-digit arrays. It stores it as a tensor. Right? Remember, a tensor just means an array with more dimensions. Okay? You can use the word array as well. It means the same thing, but in PyTorch, they always use the word tensor, so I'm going to say tensor. Okay? So it's just a tensor with an additional axis, which allows us to stack each of these filters together. Right? Filter and kernel pretty much mean the same thing here, right? It refers to one of these 3x3 matrices, or one of these 3x3 slices of a 3-dimensional tensor. So if I take this one, and here I've literally just copied the formulas in Excel from above, okay? And so you can see this one is now finding a vertical edge, as we would expect, okay? So we've now created one layer, right? This here is a layer. And specifically, we'd say it's a hidden layer, which is it's not an input layer and it's not an output layer, so everything else is a hidden layer. Okay. And this particular hidden layer has is of size 2 on this dimension, right? Because it has 2 filters, right? 2 kernels. So what happens next? Well, let's do another one. Okay, so as we kind of go along, things can multiply a little bit in complexity, right? Because my next filter is going to have to contain 2 of these 3x3s, because I'm going to have to say, how do I want to weight these 3 things, and at the same time, how do I want to weight the corresponding 3 things down here, right? Because in PyTorch, this whole thing here is going to be stored as a multidimensional tensor, right? So you shouldn't really think of this now as 2 3x3 kernels, but 1 2x3x3 kernel. Okay, so to calculate this value here, I've got the sum product of all of that plus the sum product of, let's scroll down, all of that. Okay? And so the top ones are being multiplied by this part of the kernel, and the bottom ones are being multiplied by this part of the kernel. And so over time, you want to start to get very comfortable with the idea of these like higher dimensional linear combinations, right? Like it's harder to draw it on the screen, like I had to put one above the other. But conceptually, just stack it in your mind like this. That's really how you want to think. Right? And actually, Geoffrey Hinton, in his original 2012 Neural Nets Coursera class, has a tip, which is how all computer scientists deal with like very high dimensional spaces, which is that they basically just visualize the 2-dimensional space and then say like 12 dimensions really fast in their head lots of times. So that's it, right? We can see 2 dimensions on the screen, and then you just got to try to trust that you can have more dimensions. Like the concepts just, there's nothing different about them. And so you can see in Excel, Excel doesn't have the ability to handle 3-dimensional tensors. So I had to like say, okay, take this 2-dimensional dot product, add on this 2-dimensional dot product, right? But if there was some kind of 3D Excel, I could have just done that in a single formula, right? And then again, apply max 0, otherwise known as rectified linear unit, otherwise known as ReLU. Okay, so here is my second layer. And so when people create different architectures, right, an architecture means like how big is your kernel at layer 1, how many filters are in your kernel at layer 1. So here I've got a 3x3, there's number 1, and a 3x3, there's number 2. So like this architecture I've created starts off with 2 3x3 convolutional kernels. And then my second layer has another 2 kernels of size 2x3x3. So there's the first one, and then down here, here's the second 2x3x3 kernel. Okay, and so remember, one of these specific, any one of these numbers is an activation. Okay, so this activation is being calculated from these 3 things here, another 3 things up there, and we're using this 2x3x3 kernel. Okay, and so what tends to happen is people generally give names to their layers. So I say, okay, let's call this layer here conv1, and this layer here, oopsie daisy, and this layer here conv2, right? So that's, generally you'll just see that like when you print out a summary of a network, every layer will have some kind of name, okay? And so then what happens next? Well, part of the architecture is like, do you have some max pooling? Whereabouts does that max pooling happen? So in this architecture we're inventing, we're going to, next step is do max pooling. Okay, max pooling is a little hard to kind of show in Excel, but we've got it. So max pooling, if I do a 2x2 max pooling, it's going to halve the resolution, both height and width. So you can see here that I've replaced these 4 numbers with the maximum of those 4 numbers, right? And so because I'm halving the resolution, it only makes sense to actually have something every 2 cells. Okay, so you can see here the way I've got kind of the same looking shape as I had back here, okay, but it's now half the resolution because I've replaced every 2x2 with its max. And you'll notice, like, it's not every possible 2x2. I skip over from here, so this is like starting at BQ, and then the next one starts at BS, right? So they're like non-overlapping. That's why it's decreasing the resolution. Okay, so anybody who's comfortable with spreadsheets, you can open this and have a look. And so after our max pooling, there's a number of different things we could do next, and I'm going to show you a kind of classic old-style approach. Nowadays, in fact, what generally happens nowadays is we do a max pool where we kind of like max across the entire size, right? But on older architectures and also on all the structured data stuff we do, we actually do something called a fully connected layer. And so here's a fully connected layer. I'm going to take every single one of these activations, and I'm going to give every single one of them a weight, right? And so then I'm going to take over here, here is the sum product of every one of the activations by every one of the weights for both of the 2 levels of my 3-dimensional tensor. Right? And so this is called a fully connected layer. Notice it's different to a convolution. I'm not going through a few at a time, right? But I'm creating a really big weight matrix, right? So rather than having a couple of little 3x3 kernels, my weight matrix is now as big as the entire input. And so, as you can imagine, architectures that make heavy use of fully convolutional layers can have a lot of weights. Which means they can have trouble with overfitting, and they can also be slow. And so you're going to see a lot an architecture called VGG, because it was the first kind of successful deeper architecture. It has up to 19 layers. And VGG actually contains a fully connected layer with 4,096 weights connected to a hidden layer with 4,096 activations connected to a hidden layer with 4096 activations. So you've got like 4096 by 4096 multiplied by, remember, multiplied by the number of kind of kernels that we've calculated. So in VGG, there's I think it's like 300 million weights, of which something like 250 million of them are in these fully connected layers. So we'll learn later on in the course about how we can kind of avoid using these big fully connected layers. And behind the scenes, all the stuff that you've seen us using, like ResNet and ResNext, none of them use very large fully connected layers. Yanette, you had a question.
Hi.
Sorry. Yeah, go on.
Hello. So could you tell us more about, for example, if we had like 3 channels of the input, what would be the shape of these filters?
Right. So that's a great question. So if we had 3 channels of input, it would look exactly like conv1, right? Conv1 kind of has 2 channels, right? And so you can see with conv1 we had 2 channels, so therefore our filters had to have like 2 channels per filter. And so you could like imagine that this input didn't exist, you know, and actually this was the input, right? So when you have a multi-channel input, it just means that your filters look like this. And so images often are full color. They have 3, red, green, and blue. Sometimes they also have an alpha channel. So however many you have, that's how many inputs you need. And so something which I know Yanette was playing with recently was like using a full color ImageNet model in medical imaging for something called bone age calculations, which has a single channel. And so what she did was basically take the input, the single channel input, and make 3 copies of it. So you end up with basically like 1, 2, 3 versions of the same thing, which is like, it's not ideal, like it's kind of redundant information that we don't quite want, but it does mean that then if you had something that expected a 3-channel convolutional filter, you can use it, right? And so at the moment, there's a Kaggle competition for iceberg detection using some funky satellite-specific data format that has 2 channels. So here's how you could do that. You could either copy one of those 2 channels into the 3rd channel, or I think what people on Kaggle are doing is to take the average of the 2. Again, it's not ideal, but it's a way that you can use pre-trained networks. I've done a lot of fiddling around like that. You can also I've actually done things where I wanted to use a 3-channel ImageNet network on 4-channel data. I had satellite data where the 4th channel was near infrared. And so basically I added an extra kind of level to my convolutional kernels that were all zeros. And so basically like started off by ignoring the near infrared band. And so what happens basically, and you'll see this next week, is that rather than having these like carefully trained filters when you're actually training something from scratch, we're actually going to start with random numbers. Right? That's actually what we do. We actually start with random numbers, and then we use this thing called stochastic gradient descent, which we've kind of seen conceptually, to slightly improve those random numbers to make them less random. And we basically do that again and again and again. Okay, great. Let's take a 7-minute break, and we'll come back at 7:50. All right, so what happens next? So we got as far as doing a fully connected layer, right? So we had the results of our max pooling layer got fed to a fully connected layer. And you might notice, those of you that remember your linear algebra, the fully connected layer is actually doing a classic traditional matrix product. Okay, so it's basically just going through each pair in turn, multiplying them together, and then adding them up to do a matrix product. Now, in practice, if we want to calculate which one of the 10 digits we're looking at this single number we've calculated isn't enough. We would actually calculate 10 numbers. So what we would have is, rather than just having one set of fully connected weights like this, and I say set because remember there's like a whole 3D kind of tensor of them, we would actually need 10 of those, right? So you can see that these tensors start to get a little bit high dimensional, right? And so this is where my patience with doing it in Excel ran out. But imagine that I had done this 10 times. I could now have 10 different numbers all being calculated here using exactly the same process, right? It'd just be 10 of these fully connected 2 by n arrays, basically. And so then we would have 10 numbers being spat out. So what happens next? So next up, we can open up a different Excel worksheet, entropy example.xls. That's got 2 different worksheets. One of them is called softmax. And what happens here, I've changed domains. Rather than predicting whether it's a number from 0 to 9, I'm going to predict whether something is a cat, a dog, a plane, a fish, or a building. Okay, so out of that fully connected layer, we've got, in this case, we'd have 5 numbers. And notice at this point, there's no ReLU. Okay, in the last layer, there's no ReLU. Okay, so I can have negatives. Okay, so I want to turn these 5 numbers each into a probability. I want to turn it into a probability from 0 to 1 that it's a cat, that it's a dog, that it's a plane, that it's a fish, that it's a building. And I want those probabilities to have a couple of characteristics. First is that each of them should be between 0 and 1. And the second is that they together should add up to 1, right? It's definitely one of these 5 things. Okay, so to do that, we use a different kind of activation function. What's an activation function? An activation function is a function that is applied to activations. So for example, max 0, something is a function that I applied to an activation. So an activation function always takes in one number and spits out one number. So max of 0, x takes in a number x and spits out some different number, ReLU of x. That's all an activation function is. And if you remember back to that PowerPoint we saw in lesson 1, each of our layers was just a linear function. And then after every layer, we said we needed some nonlinearity, right? Because if you stack a bunch of linear layers together, right, then all you end up with is a linear layer, right? So if somebody's talking, can you not? I'm slightly distracting. Thank you. If you stack a number of linear functions together, you just end up with a linear function. And nobody does any cool deep learning with just linear functions, right? But remember, we also learnt that by stacking linear functions with between each one a nonlinearity, we could create like arbitrarily complex shapes. And so the nonlinearity that we're using after every hidden layer is a ReLU, rectified linear unit. A nonlinearity is an activation function. An activation function is a nonlinearity. Within deep learning, obviously there's lots of other nonlinearities in the world, but in deep learning, this is what we mean. So an activation function is any function that takes some activation in, that's a single number, and spits out some new activation like max of 0, So I'm now going to tell you about a different activation function. It's slightly more complicated than ReLU, but not too much. It's called softmax. Softmax only ever occurs in the final layer, at the very end. And the reason why is that softmax always spits out numbers as an activation function that always spits out a number between 0 and 1, and it always spits out a bunch of numbers that add to 1. So a softmax gives us what we want, right? In theory, this isn't strictly necessary, right? Like we could ask our neural net to learn a set of kernels which have, which give probabilities that line up as closely as possible with what we want. But in general, with deep learning, if you can construct your architecture so that the desired characteristics are as easy to express as possible, you'll end up with better models. Like they'll learn more quickly with less parameters. So in this case, we know that our probabilities should end up being between 0 and 1. We know that they should end up adding to 1. So if we construct an activation function which always has those features, then we're going to make our neural network do a better job. It's going to make it easier for it. It doesn't have to learn to do those things because it'll happen automatically. Okay, so in order to make this work, we first of all have to get rid of all of the negatives, right? Like we can't have negative probabilities. So to make things not be negative, one way we could do it is just go e to the power of, right? So here you can see my first step is to go exp of the previous one, right? And I think I've mentioned this before, but of all the math that you just need to be super familiar with to do deep learning, the one you really need is logarithms and exps, right? All of deep learning and all of machine learning, they appear all the time, right? So, for example, you absolutely need to know that log of x times y equals log of x plus log of y, right? And like not just know that that's a formula that exists, but have a sense of like, what does that mean? Why is that interesting? Oh, I can turn multiplications into additions. That could be really handy, right? And therefore, log of x over y equals log of x minus log of y. Again, that's going to come in pretty handy, rather than dividing, I can just subtract things, right? And also remember that if I've got log of x equals y, then that means e to the y equals x. In other words, log and e to the are the inverse of each other. Okay, again, you need to really, really understand these things. And like, so if you haven't spent much time with logs and exps for a while, try plotting them in Excel or in Jupyter Notebook, have a sense of what shape they are, how they combine together. Just make sure you're really comfortable with them. So we're using it here, right? We're using it here. So one of the things that we know is that e to the power of something is positive. Okay, so that's great. The other thing you'll notice about e to the power of something is because it's a power, numbers that are slightly bigger than other numbers, like 4 is a little bit bigger than 2.8. When you go e to the power of, it really accentuates that difference. Okay, so we're going to take advantage of both of these features for the purpose of deep learning. Okay, so we take our the results of this fully connected layer, we go e to the power of for each of them, and then we're going to here we go. And then we're going to add them up. Okay, so here is the sum of e to the power of. So then here, we're going to take e to the power of divided by the sum of e to the power of. So if you take all of these things divided by their sum, then by definition, all of those things must add up to 1. And furthermore, since we're dividing by their sum, they must always vary between 0 and 1, because they are always positive. All right? And that's it. So that's what softmax is. Okay, so I've got this kind of doing random numbers each time, right? And so you can see, like, as I loop through, my softmax generally has quite a few things that are so close to 0 that they round down to 0, and maybe one thing that's nearly 1, right? And the reason for that is what we just talked about. That is, with the exp, just having one number a bit bigger than the others tends to like push it out further, right? So even though my inputs here are random numbers between -5 and 5, right? my outputs from the softmax don't really look that random at all, in the sense that they tend to have one big number and a bunch of small numbers. And now that's what we want, right? We want to say, like, in terms of, like, is this a cat, a dog, a plane, a fish, or a building? We really want it to say, like, it's that, you know, it's a dog or it's a plane, not like, I don't know. Okay, so softmax has lots of these cool properties, right? It's going to return a probability that adds up to 1, and it's going to tend to want to pick one thing particularly strongly. Okay, so that's softmax. Yannick, could you pass, actually pass it to me, I'll pass it away.
How would we do something that has, let's say you have an image and you want to categorize it as like cat and a dog, or like has multiple things. What kind of function would we try to use?
So happens we're going to do that right now. So have to think about why we might want to do that. And so one reason we might want to do that is to do multi-label classification. So we're looking now at lesson 2 image models. And specifically, we're going to take a look at the planet competition, satellite imaging competition. Now, the satellite imaging competition has some similarities to stuff we've seen before, right? So before, we've seen cat versus dog. And these images are a cat or a dog. They're not neither, they're not both, right? But the satellite imaging competition has images that look like this. And in fact, every single one of the images is classified by weather. There's 4 kinds of weather, one of which is haze, and another of which is clear. In addition to which, there is a list of features that may be present, including agriculture, which is like some cleared area used for agriculture, primary, which means primary rainforest, and water, which means a river or a creek. So here is a clear day satellite image showing some agriculture, some primary rainforest, and some water features. And here's one which is in haze and is entirely primary rainforest. So in this case, we're going to want to be able to show, we're going to be able to predict multiple things. And so softmax wouldn't be good, because softmax doesn't like predicting multiple things. And like, I would definitely recommend anthropomorphizing your activation functions, right? They have personalities, okay? And the personality of the softmax is it wants to pick a thing, okay? And people forget this all the time. I've seen many people, even well-regarded researchers in famous academic papers, using like softmax for multi-label classification. It happens all the time, right? And it's kind of ridiculous, because they're not understanding the personality of their activation function. So for multi-label classification, where each sample can belong to one or more classes, we have to change a few things. But here's the good news. In FastAI, we don't have to change anything. Right? So FastAI will look at the labels in the CSV, and if there is more than one label ever for any item, it will automatically switch into like multi-label mode. So I'm going to show you how it works behind the scenes, but the good news is you don't actually have to care, right? It happens anyway. So if you have multi-label images, multi-label objects, you obviously can't use the classic Keras style approach where things are in folders, because something can't conveniently be in multiple folders at the same time, right? So that's why you basically have to use the from CSV approach, right? So if we look at an example, actually I'll show you, I'll try to take you through it, right? So we can say, okay, this is the CSV file containing our labels. This looks exactly the same as it did before, but rather than side on, it's top down, right? And top down, I've mentioned before that it can do vertical flips. It actually does more than that. There's actually 8 possible symmetries for a square, which is it can be rotated through 90, 180, 270, or 0 degrees. and for each of those it can be flipped. And if you think about it for a while, you'll realize that that's a complete enumeration of everything that you can do in terms of symmetries to a square. So it's called the dihedral group of 8. So if you see in the code, there's actually a transform called dihedral. That's why it's called that. So this transforms will basically do the full set of 8 symmetric dihedral rotations and flips, plus everything which we can do to dogs and cats. Small 10-degree rotations, a little bit of zooming, a little bit of contrast and brightness adjustment. So these images are of size 256 by 256. So I just created a little function here to let me quickly grab, a data loader of any size. So here's a 256 by 256. Once you've got a data object, inside it, we've already seen that there's things called val ds, test ds, train ds. They're things that you can just index into and grab a particular image. So you can just use square brackets 0. You'll also see that all of those things have a DL. That's a data loader. So DS is data set, DL is data loader. These are concepts from PyTorch. So if you Google PyTorch data set or PyTorch data loader, you can basically see what it means. But the basic idea is a data set gives you a single image or a single object back. A data loader gives you back a mini batch. And specifically, it gives you back a transformed mini batch. So that's why when we create our data object, we can pass in num workers and transforms, like how many processes do you want to use, what transforms do you want. And so with a data loader, you can't ask for an individual image, you can only get back a mini batch. And you can't get back a particular mini batch, you can only get back the next mini batch. So something where you're just going to loop through, grabbing a mini batch at a time. And so in Python, the thing that does that is called a generator, right? Or an iterator. There's slightly different versions of the same thing. So to turn a data loader into an iterator, you use the standard Python function called iter. That's a Python function, just a regular part of the Python basic language that returns you an iterator. And an iterator is something that you can pass it to the standard Python function or statement next, and that just says, give me another batch from this iterator. So we're basically, this is one of the things I really like about PyTorch, is it really leverages modern Python's kind of stuff. In TensorFlow, they invent their whole new world of ways of doing things. And so it's kind of more, in a sense, it's more like cross-platform, but in another sense, like it's not a good fit to any platform. So it's nice. If you know Python well, PyTorch comes very naturally. If you don't know Python well, PyTorch is a good reason to learn Python well. A PyTorch neural network module is a standard Python class, for example. So any work you put into learning Python better will pay off with PyTorch. So here I am using standard Python iterators and next to grab my next mini batch from the validation sets data loader. And that's going to return two things. It's going to return the images in the mini batch and the labels in the mini batch. So standard Python approach, I can pull them apart like so. And so here is one mini batch of labels. And so not surprisingly, since I said that my batch size, let's go back and find it. Actually, it's the batch size by default is 64. So I didn't pass in a batch size. So just remember, Shift Tab to see like what are the things you can pass and what are the defaults. So by default, my batch size is 64. So I've got back something of size 64 by 17. So there are 17 of the possible classes, right? So let's take a look at the 0th set of labels. So the 0th images labels. So I can zip, again, standard Python thing, zip takes two lists and combines it. So you get the 0th thing from the first list, the 0th thing from the second list, and the first thing from the first list, first thing from the second list, and so forth. So I can zip them together, and that way I can find out for the 0th image in the validation set it's agriculture, it's clear, it's primary rainforest, it's slash and burn, it's water. Okay, so as you can see here, this is a multi-label. Here's a way to do multi-label classification. So by the same token, right, if we go back to our single label classification, it's a cat, dog, plane, fish, or building, behind the scenes, we haven't actually looked at it, but behind the scenes, FastAI and PyTorch are turning our labels into something called one-hot encoded labels. And so if it was actually a dog, then the actual values would be like that, right? So these are like the actuals. Okay, so do you remember at the very end of Ottavio's video, he showed how like the template had to match to one of the like 5 A, B, C, D, or E templates. And so what it's actually doing is it's comparing, when I said it's basically doing a dot product, it's actually a fully connected layer at the end, right? That calculates an output activation. It goes through a softmax, and then the softmax is compared to the one hot encoded label, right? So if it was a dog, there would be a 1 here. And then we take the difference between the actuals and the softmax activations to say, and add up those differences to say how much error is there, essentially. We're skipping over something called a loss function that we'll learn about next week, but essentially we're basically doing that. Now, if it's one hot encoded, like if there's only one thing which have a 1 in it, then actually storing it as 0, 1, 0, 0, 0 is terribly inefficient, right? Like we could basically say, what are the index of each of these things, right? So we can say it's like 0, 1, 2, 3, 4, like so, right? And so rather than storing it as 0, 1, 0, 0, 0, we actually just store the index value, right? So if you look at the Y values for the cats and dogs competition or the dog breeds competition, you won't actually see a big list of 1s and 0s like this. You'll see a single integer, right? Which is like what class index is it, right? And internally, inside PyTorch, it will actually turn that into a one hot encoded vector, but like you will literally never see it. Okay, and PyTorch has different loss functions where you basically say this thing is one hot encoded or this thing is not, and it uses different loss functions. That's all hidden by the FastAI library, right? So like you don't have to worry about it. But the cool thing to realize is that this approach for multi-label encoding with these 1s and 0s, behind the scenes, the exact same thing happens for single label classification. Could you pass that back?
Does it make sense to change the pickiness of the sigmoid of the softmax function by changing the base?
No, because when you change the more math, log base A of B equals log B over log A. So changing the base is just a linear scaling, and linear scaling is something which the neural net can learn with very easily. Good question. Okay, so here is that image, right? Here is the image with slash and burn, water, etc., etc. One of the things to notice here is like when I first displayed this image, it was so washed out, I really couldn't see it, right? But remember, images, now, we know images are just matrices of numbers. And so you can see here, I just said times 1.4, just to make it more visible, right? So like now that you're it's the kind of thing I want you to get familiar with is the idea that this stuff you're dealing with, they're just matrices of numbers and you can fiddle around with them. So if you're looking at something and you're like, oh, it's a bit washed out, you can just multiply it by something to brighten it up a bit. Okay. So here we can see, I guess this is the slash and burn. Here's the river, that's the water. Here's the primary rainforest. Maybe that's the agriculture and so forth. Okay. So, you know, with all that background, how do we actually use this? Exactly the same way as everything we've done before, right? So, you know, size, you know, and the interesting thing about playing around with this planet competition is that these images are not at all like ImageNet. And I would guess that the vast majority of the stuff that the vast majority of you do involving convolutional neural nets won't actually be anything like ImageNet. You know, it'll be medical imaging, or it'll be like classifying different kinds of steel tube, or figuring out whether a weld, you know, is going to break or not, or looking at satellite images, or, you know, whatever, right? So it's good to experiment with stuff like this planet competition to get a sense of kind of what you want to do. And so you'll see here, I start out by resizing my data to 64 by 64. It starts out at 256 by 256, right? Now, I wouldn't want to do this for the cats and dogs competition, because the cats and dogs competition, we start with a pre-trained ImageNet network. It starts off nearly perfect, right? So if we resized everything to 64 by 64 and then retrained the whole set, we basically destroy the weights that are already pre-trained to be very good. Remember, most ImageNet models are trained at either 224 by 224 or 299 by 299, right? So if we like retrain them at 64 by 64, we're gonna kill it. On the other hand, there's nothing in ImageNet that looks anything like this. You know, there's no satellite images. So the only useful bits of the ImageNet network for us are kind of layers like this one, you know, finding edges and gradients, and this one, you know, finding kind of textures and repeating patterns. And maybe these ones of kind of finding more complex textures, but that's probably about it, right? So in other words, you know, starting out by training very small images works pretty well when you're using stuff like satellites. So in this case, I started right back at 64 by 64, grabbed some data, built my model, found out what learning rate to use. Interestingly, it turned out to be quite high. It seems that because like it's so unlike ImageNet, I needed to do quite a bit more fitting of just that last layer before it started to flatten out. Then I unfreezed it. And again, this is the difference to ImageNet-like data sets, is my learning rate in the initial layer I set to divided by 9, the middle layers I set to divided by 3, where else for stuff like ImageNet I had a multiple of 10 for each of those. You know, again, the idea being that the earlier layers probably are not as close to what they need to be compared to the ImageNet-like data sets. So again, unfreeze, train for a while, and you can kind of see here, you know, there's cycle 1, there's cycle 2, there's cycle 3, and then I kind of increase, double the size of my images, fit for a while, unfreeze, fit for a while, double the size of the images again, fit for a while, unfreeze, fit for a while, and then add TTA. And so as I mentioned last time we looked at this, this process ends up, you know, getting us about 30th place in this competition, which is really cool because people, you know, a lot of very, very smart people just a few months ago worked very, very hard on this competition. Couple of things people have asked about. One is, what does this data.resize do? A couple of different pieces here. The first is that when we say back here, what transforms do we apply? And here's our transforms. We actually pass in a size, right? So one of the things our data loader does is to resize the images like on demand every time it sees them. This has got nothing to do with that .resize method, right? So this is the thing that happens at the end. Like whatever's passed in before it hits before our data loader spits it out, it's going to resize it to this size. if the initial input is like 1,000 by 1,000, reading that JPEG and resizing it to 64 by 64 turns out to actually take more time than training the ConvNet does for each batch, right? So basically, all resize does is it says, hey, I'm not going to be using any images bigger than size times 1.3. So just go through once and create new JPEGs of this size, right? And they're rectangular, right? So new JPEGs where the smallest edge is of this size. And again, it's like you never have to do this. There's no reason to ever use it if you don't want to. It's just a speed up. Okay, but if you've got really big images coming in, it saves you a lot of time. And you'll often see on like Kaggle kernels or forum posts or whatever, people will have like bash scripts or stuff like that to like loop through and resize images to save time. You never have to do that, right? You can just say .resize and it'll just create, once off, it'll go through and create that. If it's already there, it'll use the resized ones for you. Okay, so it's just a speed up convenience function, no more. Okay, so for those of you that are kind of past dog breeds, I would be looking at Planet next. Play around with trying to get a sense of like how can you get this as an accurate model. One thing to mention, and I'm not really going to go into it in detail because it's nothing to do with deep learning particularly, is that I'm using a different metric. I didn't use metrics equals accuracy, but I said metrics equals F2. Just remember from last week that confusion matrix, that like 2 by 2, correct, incorrect for each of dogs and cats. There's a lot of different ways you could turn that confusion matrix into a score. Do you care more about false negatives or do you care more about false positives, and how do you weight them and how do you combine them together, right? There's basically a function called f beta, where the beta says how much do you weight false negatives versus false positives. And so F2 is f beta with beta equals 2. And it's basically a particular way of weighting false negatives and false positives. And the reason we use it is because Kaggle told us that Planet, who are running this competition, wanted to use this particular f beta metric. The important thing for you to know is that you can create custom metrics. So in this case, you can see here it says from Planet import F2. And really, I've got this here so that you can see how to do it, right? So if you look inside courses DL1, you can see there's something called planet.py, right? And so if I look at planet.py, you'll see there's a function there called F2, right? And so F2 simply calls F beta score from scikit or scipy, I can't remember where it came from, and does a couple of little tweaks that are particularly important. But the important thing is, like, you can write any metric you like, right? As long as it takes in a set of predictions and a set of targets, and they're both going to be NumPy arrays, one-dimensional NumPy arrays, and then you return back a number. Okay, and so as long as you create a function that takes 2 vectors and returns a number, you can call it as a metric. And so then when we said, let's see here, learn metrics equals, and then passed in that array, which just contains a single function, F2, then it's just going to be printed out after every epoch for you. Okay, so in general, like the FastAI library, everything is customizable. So kind of the idea is that everything is kind of gives you what you might want by default, but also everything can be changed as well. Yes, Yannette.
We have a little bit of confusion about the difference between multi-label and just single label. Do you have by any chance an example in which you compute, like similarly to the example of that you just showed us?
I didn't get to that. Yeah, activation function. Yeah. So I'm so sorry. I said I'd do that and then I didn't. So the output activation function for single label classification is softmax for all the reasons that we talked about. But if we were trying to predict something that was like 0, 0, 1, 1, 0, then softmax would be a terrible choice because it's very hard to come up with something where both of these are high. In fact, it's impossible because they have to add up to 1, so the closest they could be would be 0.5. So for multi-label classification, our activation function is called sigmoid. Okay, and again, the FastAI library does this automatically for you if it notices you have a multi-label problem, and it does that by checking your data set to see if anything has more than one label applied to it. And so sigmoid is a function which is equal to, it's basically the same thing, except rather than, we never add up all of these exps, but instead we just take this exp and we say it's just equal to it divided by 1 plus it. And so the nice thing about that is that now, like, multiple things can be high at once, right? And so generally then, if something is less than 0, its sigmoid is going to be less than 0.5. If it's greater than 0, its sigmoid is going to be greater than 0.5. And so the important thing to know about a sigmoid function is that its shape is something which asymptotes at the top to 1 and asymptotes, oh, I drew that. Asymptotes at the bottom to 0. And so therefore it's a good thing to model a probability with. Anybody who has done any logistic regression will be familiar with this. It's what we do in logistic regression. So it kind of appears everywhere in machine learning. And you'll see that kind of a sigmoid and a softmax, they're very close to each other, kind of conceptually. But this is what we want as our activation function for multi-label. And this is what we want for single label. And again, FastAI does it all for you. There was a question over here. Yes.
I have a question about the initial training that you do. If I understand correctly, you have frozen the pre-trained model, and you only initially try to train the latest layer, right?
Right.
But from the other hand, we said that only the initial layer, so probably the first layer, is like important to us, and the other two are more like features that are ImageNet related and wouldn't apply in this case?
Well, the layers are very important, but the pre-trained weights in them aren't. So it's the later layers that we really want to train the most. The earlier layers are likely to be like already closer to what we want.
Okay, so you start with the latest one and then you go to
right. So if you go back to our quick dogs and cats, right? When we create a model from a pre-trained model, it returns something where all of the convolutional layers are frozen and some randomly set fully connected layers we add to the end are unfrozen. And so when we go fit, at first it just trains the randomly initialized fully connected layers, right? And if something is like really close to ImageNet, that's often all we need, right? Because the earlier layers are already good at finding edges, gradients, repeating patterns, fur, ears, and dogs' heads, you know. So then when we unfreeze, we set the learning rates for the early layers to be really low because we don't want to change them much, whereas the later ones, we set them to be higher. Where else for satellite data, right, this is no longer true. You know, the early layers are still like better than the later layers, but we still probably need to change them quite a bit. So that's why this learning rate is 9 times smaller than the final learning rate, rather than 1,000 times smaller than the final learning rate.
Okay, so you play with the weights of the layers, with the learning rates. Okay.
Yeah, normally, most of the stuff you see online, if they talk about this at all, they'll talk about unfreezing different subsets of layers. And indeed, we do unfreeze our randomly generated ones. But what I've found is, although the FastAI library, you can type learn.freeze2 and just freeze a subset of layers, this approach of using differential learning rates seems to be like more flexible to the point that I never find myself unfreezing subsets of layers.
So, but what I don't understand is that I would expect you to start with that, with the different learning rates, rather than trying to learn the last layer.
So the reason, okay, so you could skip this training just the last layers and just go straight to differential learning rates. But you probably don't want to. And the reason you probably don't want to is that there's a difference. The convolutional layers all contain pre-trained weights. So they're not random. For things that are close to ImageNet, they're actually really good. For things that are not close to ImageNet, they're better than nothing. All of our fully connected layers, however, are totally random. So therefore, you would always want to make the fully connected weights better than random by training them a bit first, because otherwise, if you go straight to unfreeze, then you're actually going to be like fiddling around with those early layer weights when the later ones are still random. That's probably not what you want. I think there's another question here. Can you pass it over?
So when we unfreeze, what are the things we are trying to change there? Will it change the kernels themselves, or
that's always what SGD does. Yeah. So the only thing, what training means is setting these numbers, right, and these numbers, and these numbers, the weights. So the weights are the weights of the fully connected layers and the weights in those kernels in the convolution. So that's what training means. And we'll learn about how to do it with SGD, but training literally is setting those numbers. These numbers, on the other hand, are activations. They're calculated. And they're calculated from the weights and the previous layers, activations or inputs.
I have a question. So,
can you lift that up higher and speak loudly?
So, in your example of training the satellite image example, so you start with very small size, like 64.
Yeah.
So, does it literally mean that the model takes a small area from the entire image that is 64 by 64?
So how do we get that 64 by 64 depends on the transforms. By default, our transform takes the smallest edge and zooms the whole thing out, resamples it, so the smallest edge is the size 64, and then it takes a center crop of that. Okay, although when we're using data augmentation, it actually takes a randomly chosen crop.
But in the case where like an image has multiple objects, like in this case, like would it be possible, like you would just lose the other things that they try to predict?
Yeah, which is why data augmentation is important. So and particularly their test time augmentation is going to be particularly important, because you wouldn't want to, there may be a artisanal mine out in the corner, which if you take a center crop, you don't see. So data augmentation becomes very important here.
Got it. I actually have one other question.
Sure.
So when we talk about metrics, like either it's accuracy, like null or F2, that's not really what the model tries to optimize.
That's a great point. That's not the loss function.
Yeah.
Right. The loss function is something we'll be learning about next week. And it uses cross entropy, or otherwise known as negative log likelihood. The metric is just the thing that's printed, so we can see what's going on. Just next to you.
So in the context of multi-class modeling, does our training data also have to be multi-class, or can I train on just like images of pure cats and pure dogs and expect it at prediction time to predict if I give it a picture of both having cat and a dog?
I've never tried that, and I've never seen an example of something that needed it. I guess conceptually there's no reason it wouldn't work, but it's kind of out there.
Okay. And you still use a sigmoid activation?
You would have to make sure you're using a sigmoid loss function. So in this case, FastAI's default would not work, because by default, FastAI would say your training data never has both a cat and a dog, so you would have to override the loss function.
Thanks.
Yeah. Was there another one just behind you?
When you use the differential learning rates, those 3 learning rates, do they just kind of spread evenly across the layers?
Yeah, we'll talk more about this later in the course, but in the FastAI library, there's a concept of layer groups. So in something like a ResNet 50, there's hundreds of layers, and I figured you don't want to write down hundreds of learning rates. So I've basically decided for you how to split them, and the last one always refers just to the fully connected layers that we've randomly initialized and added to the end. And then these ones are split generally about halfway through. Basically, I've tried to make it so that these ones are kind of the ones which you hardly want to change at all, and these are the ones you might want to change a little bit. And I don't think we'll cover it in the course, but if you're interested, we can talk about it in the forum. There are ways you can override this behavior to define your own layer groups if you want to.
And is there any way to visualize the model easily, or like dump the layers of the model?
Yeah, absolutely. You can, let's make sure we've got one here. Okay. So if you just type learn, it doesn't tell you much at all, but what you can do is go learn.summary, and that spits out basically everything. There's all the layers. And so you can see in this case, these are the names. I mentioned how they all got names, right? So the first layer is called conv2d-1, and it's going to take as input. This is useful to actually look at. It's taking 64 by 64 images, which is what we told it we're going to transform things to. This is 3 channels. PyTorch, like most things have channels at the end, would say 64 by 64 by 3. PyTorch moves it to the front. So it's 3 by 64 by 64. That's because it turns out that some of the GPU computations run faster when it's in that order. Okay, but that happens all behind the scenes automatically. So part of that transformation stuff that's kind of all done automatically is to do that. -1 means however big the batch size is. In Keras, they use the number. They use a special number none. In PyTorch, they use -1. So this is a 4-dimensional mini batch. The number of elements in the number of images in the mini batch is dynamic. You can change that. The number of channels is 3. The number of images is 64 by 64. Okay, and so then you can basically see that this particular convolutional kernel apparently has 64 kernels in it, and it's also halving. We haven't talked about this, but convolutions can have something called a stride. It's like max pooling. It changes the size. So it's returning a 32 by 32 by 64 kernel tensor, and so on and so forth. So that's summary. And we'll learn all about what that's doing in detail in the second half of the course.
One more. I collected my own data set, and I tried to use and it was a really small data set, these currencies from Google Images. And I tried to do a learning rate find and then the plot, and it it gave me some numbers which I didn't understand on the learning rate font.
Yeah.
And then the plot was empty. So does that mean?
Let's talk about that on the forum. But basically, the learning rate finder is going to go through a mini batch at a time. If you've got a tiny data set, there's just not enough mini batches. So the trick is to make your batch size really small. Like try making it like 4 or 8 or something. Okay, they were great questions. Nothing online to add, Jeanette? They were great questions. We've gone a little bit past where I hoped to, but let's quickly talk about structured data so we can start thinking about it for next week. So this is really weird, right? To me, there's basically 2 types of data set we use in machine learning. There's a type of data like audio, images, natural language text, where all of the things inside an object, like all of the pixels inside an image, are all the same kind of thing. They're all pixels, or they're all amplitudes of a waveform, or they're all words. I call this kind of data unstructured. And then there's data sets like a profit and loss statement, or the information about a Facebook user, where each column is like structurally quite different. You know, one thing is representing like how many page views last month, another one is their sex, another one is what zip code they're in. And I call this structured data. That particular terminology is not unusual, like lots of people use that terminology, but lots of people don't. There's no particularly agreed upon terminology. So when I say structured data, I'm referring to kind of columnar data as you might find in a database or a spreadsheet where different columns represent different kinds of things and each row represents an observation. And so structured data is probably what most of you are analyzing most of the time. Funnily enough, you know, academics in the deep learning world don't really give a shit about structured data because it's pretty hard to get published in fancy conference proceedings if you've got a better logistics model. You know, it's the thing that makes the world goes round. It's the thing that makes everybody, you know, money and efficiency and makes stuff work. But it's largely ignored, sadly. So we're not going to ignore it because we're practical deep learning. And Kaggle doesn't ignore it either because people put prize money up on Kaggle to solve real world problems. So there are some great Kaggle competitions we can look at. There's one running right now, which is the grocery sales forecasting competition for Ecuador's largest chain. It's always I've got to be a little careful about how much I show you about currently running competitions because I don't want to, you know, help you cheat. But it so happens there was a competition a year or two ago for one of Germany's largest grocery chains, which is almost identical. So I'm going to show you how to do that. So that was called the Rossmann stores data. And so I would suggest, you know, first of all, try practicing what we're learning on Rossmann, right? But then see if you can get it working on grocery, because currently on the leaderboard, no one seems to basically know what they're doing in the groceries competition. If you look at the leaderboard, let's see, here we are. These ones around 529, 530 are people that are literally finding like group averages and submitting those. I know because they're kernels that they're using. So, you know, basically the people around 20th place are not actually doing any machine learning. So yeah, let's see if we can improve things. So you'll see there's a lesson 3 Rossmann notebook. Make sure you git pull. Okay. In fact, you know, just reminder, you know, before you start working, git pull in your FastAI repo, and from time to time, conda env update. For you guys doing the in-person course, the conda env update, you should do it more often because we're kind of changing things a little bit. Folks in the MOOC, you know, more like once a month should be fine. So anyway, I just changed this a little bit. So make sure you git pull to get lesson 3 Rossmann. And there's a couple of new libraries here. One is fastai.structured. Fastai.structured contains stuff which is actually not at all PyTorch specific. We actually use that in the machine learning course as well for doing random forests with no PyTorch at all. I mention that because you can use that particular library without any of the other parts of FastAI. So that can be handy. And then we're also going to use fastai.column data, which is basically some stuff that allows us to do FastAI PyTorch stuff with columnar structured data. For structured data, we need to use pandas a lot. Anybody who's used R data frames will be very familiar with pandas. Pandas is basically an attempt to kind of replicate R data frames in Python, and a bit more. If you're not entirely familiar with pandas, there's a great book which I think I might have mentioned before, Python for Data Analysis by Wes McKinney. There's a new edition that just came out a couple of weeks ago. Obviously, being by the pandas author, its coverage of pandas is excellent, but it also covers NumPy, SciPy, Matplotlib, scikit-learn, IPython, and Jupyter really well. Okay, and so I'm kind of going to assume that you know your way around these libraries to some extent. Also, there was the workshop we did before this started, and there's a video of that online where we kind of have a brief mention of all of those tools. Structured data is generally shared as CSV files. It was no different in this competition. As you'll see, there's a hyperlink to the Rossmann dataset here. Right? Now, if you look at the bottom of my screen, you'll see this goes to files.fast.ai. Because this doesn't require any login or anything, to grab this dataset, it's as simple as right-clicking, copy link address, head over to wherever you want it, and just type wget and the URL. Okay? So that's because, it's not behind a login or anything. So you can grab it from there, and you can always read a CSV file with just pandas.readCSV. Now, in this particular case, there's a lot of pre-processing that we do. And what I've actually done here is I've actually stolen the entire pipeline from the third place winner of Rossmann. Okay, so they made all their data, they're really great. They made a GitHub available with everything that we need, and I've ported it all across and simplified it and tried to make it pretty easy to understand. This course is about deep learning, not about data processing, so I'm not going to go through it. But we will be going through it in the machine learning course in some detail, because feature engineering is really important. So if you're interested, check out the machine learning course for that. I will, however, show you kind of what it looks like. So once we read the CSVs in, you can see basically what's there. So the key one is for a particular store, we have let's have a look. We have the date and we have the sales for that particular store. We know whether that thing is on promo or not. We know the number of customers that particular store had. We know whether that date was a school holiday. We also know what kind of store it is. So this is pretty common, right? You'll often get data sets where there's some column with just some kind of code. We don't really know what the code means. Most of the time I find it doesn't matter what it means. Normally you get given a data dictionary when you start on a project, and obviously if you're working on an internal project, you can ask the people at your company, what does this column mean? I kind of stay away from learning too much about it. I prefer to see what the data says first. There's something about what kind of product are we selling in this particular row. And then there's information about like how far away is the nearest competitor, how long have they been open for, how long has the promo been on for. For each store, we can find out what state it's in. For each state, we can find out the name of the state. This is in Germany. And interestingly, they were allowed to download any data, external data they wanted in this competition, which is very common, as long as you share it with everybody else. And so some folks tried downloading data from Google Trends. I'm not sure exactly what it was that they were checking the trend of, but we have this information from Google Trends. Somebody downloaded the weather for every day in Germany, for every state. And yeah, that's about it, right? So you can get a data frame summary with pandas, which kind of lets you see how many observations and means and standard deviations. Again, I don't do a hell of a lot with that early on, but it's nice to know it's there. So what we do, this is called a relational data set. A relational data set is one where there's quite a few tables we have to join together. It's very easy to do that in pandas. There's a thing called merge, so I create a little function to do that. And so I just started joining everything together. I was joining the weather, the Google Trends, the stores. Yeah, that's about everything, I guess. You'll see there's one thing that I'm using from the FastAI library, which is called add date part. We talk about this a lot in the machine learning course, but basically this is going to take a date and pull out of it a bunch of columns. Day of week, is at the start of a quarter, month of year, so on and so forth, and add them all into the data set. Okay, so this is all standard pre-processing. All right, so we join everything together. We fiddle around with some of the dates a little bit. Some of them are in month and year format. We turn it into date format. We spend a lot of time trying to take information about, for example, holidays and add a column for like how long until the next holiday, how long has it been since the last holiday, ditto for promos, so on and so forth. Okay, so we do all that, and at the very end, we basically save a big structured data file that contains all that stuff. Something that those of you that use pandas may not be aware of is that there's a very cool new format called Feather, which you can save a pandas data frame into this Feather format. It's kind of pretty much takes it as it sits in RAM and dumps it to the disk. So it's like really, really, really fast. The reason that you need to know this is because the Ecuadorian grocery competition that's on now has 350 million records. So you will care about how long things take. It took, I believe, about 6 seconds for me to save 350 million records to Feather format. So that's pretty cool. So at the end of all that, I'd save it as Feather format. And for the rest of this discussion, I'm just going to take it as given that we've got this nicely pre-processed, feature-engineered file, and I can just go read Feather. Okay. But for you to play along at home, you will have to run those previous cells. Oh, except see these ones I've commented out? You don't have to run those because the file that you download from files.fast.ai has already done that for you. Okay? All right. So we basically have all these columns. So it basically is going to tell us, how many of this thing was sold on this date at this store. And so the goal of this competition is to find out how many things will be sold for each store, for each type of thing in the future. Okay? And so that's basically what we're going to be trying to do. And so here's an example of what some of the data looks like. And so next week, we're going to see how to go through these steps. But basically what we're going to learn is we're going to learn to split the columns into two types. Some columns we're going to treat as categorical, which is to say store ID 1 and store ID 2 are not numerically related to each other. They're categories, right? We're going to treat day of week like that too. Monday and Tuesday, day 0 and day 1, not numerically related to each other. Or else distance in kilometers to the nearest competitor, that's a number that we're going to treat numerically, right? So in other words, the categorical variables, we basically are going to one-hot encode them. You can think of it as one-hot encoding them. Whereas the continuous variables, we're going to be feeding into fully connected layers just as is. Okay? So what we'll be doing is we'll be basically creating a validation set, and you'll see like a lot of these will start to look familiar. This is the same function we used on Planet and Dogbreeds to create a validation set. There's some stuff that you haven't seen before where we're going to basically, rather than saying image data dot from CSV, we're going to say columnar data from data frame. Right? So you can see like the basic API concepts will be the same, but they're a little different, right? But just like before, we're going to get a learner, and we're going to go LR find to find our best learning rate, and then we're going to go .fit with a metric, with a cycle length. Okay, so the basic sequence is going to end up looking, hopefully, very familiar. Okay, so we're out of time. So what I suggest you do this week is like try to enter as many Kaggle image competitions as possible. Like try to really get this feel for like cycle lengths, learning rates, plotting things. You know, that post I showed you at the start of class today that kind of took you through lesson 1, like really go through that on as many image data sets as you can to just feel really comfortable with it. Right? Because you want to get to the point where next week, when we start talking about structured data, that this idea of like how learners kind of work and data works and data loaders and data sets and looking at pictures should be really, you know, intuitive. All right, good luck. See you next week.